Okay, welcome to Newton's Laws. In these lectures, we're going to be talking about the application of using Newton's laws to solve problems. So we're going to be applying the first, second, and third laws to solve specific or different types of force problems. So in doing this, what I would like you to do is make sure you have notebook paper available. You'll need your colored pencils, and you will need a ruler. So make sure you have all those materials. If you don't have them, please pause the video, go get them, and then we're ready to get started. Okay, so for the first example, we have a block which has a mass of capital M. It's hanging from a string at rest. We want to know what is the tension in the string, and how does the problem change if we lift it up at a constant velocity. Okay, so the first thing we're going to do in solving this problem is we're going to go ahead and draw our motion diagram and our free body diagram. In this case, the motion diagram is pretty straightforward. Okay, the motion diagram is going to have your velocity vector, which is a dot, and we're going to have our acceleration vector. And excuse the pink, it says pale purple, but it looks pink to me. But just keep in mind that's supposed to be purple. Okay, so that's our motion diagram. The block is at rest. It's hanging from a string. Okay, so now we're going to draw our free body diagram. In order to draw the free body diagram, we're going to use what we learned in the forces inquiry. But in order to do that, we're not going to draw the whole object. We're just going to draw that center dot. That's all we really need in order to draw a free body diagram. We're basically saying, let's take all the mass of our object and have it work or have it exist at a single point in space. And then let's look at the forces that act on it. Okay, so if we look at the problem here, it says a block hangs from a string at rest. What is the tension? Okay, so the first thing we're going to do is answer the two questions. What's physically touching? And what's acting at a distance? Okay, so what is physically touching? The rope. What's acting at a distance? The earth. Are we in equilibrium? Yes, we're at rest. Okay, so I know I have two forces, and I know that they have to be equal in magnitude but oppositely directed so that I am in equilibrium. So what I'm going to do now is I'm going to go ahead and draw my line. Oops. This is not a very stiff ruler. Okay, so now I'm going to label the forces. So this is force on block by earth, and this is force on block by string. Okay, so now I have my free body diagram and my motion diagram. Now I'm ready to apply Newton's second law formally. So we write the sum of the forces is equal to ma. Since I'm only working in one direction, I only need to include this for one direction. So I'm going to go ahead and put subscript y to indicate that I'm working in the vertical direction in this problem. Okay, so once we do that, we're then going to substitute in here all of the forces acting on the block. Okay, so I'm going to have force on block by string plus, because that's what summation means, add them together, force on block by earth, and that is equal to capital M A. Okay, so that's your first step, is to write out the forces acting on the block from your free body diagram, set it equal to ma. Notice I've replaced the lowercase m with the capital M because that's what they tell us in the problem here. They say that the lowercase m is equal to capital M. Oh, wrong problem here. Lowercase m is equal to capital M. Okay, now I have to ask myself, am I in equilibrium? Look at your motion diagram, look at your free body diagram. Both of those should match in telling you whether you are in equilibrium or not. Since my velocity is 0, my acceleration is 0, this acceleration is 0, I am in equilibrium. So I'm going to cross this out and put a 0, and then I'm going to write n1. And the reason I write n1 next to this is I'm showing myself, yes, Dr. H, you have applied Newton's first law in order to solve this problem. Okay, if I don't put the n1, I can't be sure when I finish the problem that I've actually applied it and have actually determined whether I have acceleration or not. Okay, so the next step we're going to do is we're going to substitute in magnitude and direction. So next, substitute magnitude and direction. Now, keep in mind that this is the tension as defined for us in class the other day, and this is the weight. Technically speaking, we don't have to substitute in the magnitude and direction at this point, but it's tricky. You have to figure out what is it that you're solving for. Do you need it as a vector? Are you going to need it as a scalar equation in order to substitute it into another direction? So here's the hint. If you're working in one direction only, you don't really need to do the magnitude and direction portion of this. Or you could do it on one side and not the other. Okay? But it can be confusing to figure that out initially when you're first learning this. So what I like to do is I just go ahead and substitute in the magnitude and direction for everything, and then I work my way backwards if I really need it to be a vector quantity. So please bear with me. If you understand what I'm talking about, we're solving for the tension, which needs to be a vector. We could easily just subtract this from both sides and then substitute in the equation. Okay? But I want to make sure that I'm prepping you for future problems that are going to be more complicated. So that's why I'm substituting in the magnitude and direction at this point. Okay, so we end up with force on block by string, and it's going in the j hat direction, minus mg j hat, because that's going down, and that's equal to 0 j hat. Okay? Now, here's the neat thing. All these j hats, they cancel out from both sides. Okay? Now I'm going to add mg to both sides. So I end up with force on block by string is equal to mg, which just happens to be the magnitude of the weight. Now, in most cases, if they say, what is the magnitude of the tension, you're done. This is the magnitude. If they ask you for the tension, this is where it gets tricky, okay? Some textbooks will ask you for the tension, but what they're really saying is, I just want the magnitude of the tension. Sometimes they'll be clear and they'll say magnitude and direction. Sometimes they're not clear. So what I would suggest you do is if they say, what is the tension, assume that you need magnitude plus direction. Since this problem here is asking us, what is the tension in the string, and it's not saying what is the magnitude of the tension, we're going to go ahead and give this a direction. So which way is the tension going? It's going up according to our diagram. So now I'm going to put F on block by string is equal to mg j hat. Now you may be saying, Dr. H, whoa, wait a minute, isn't that negative j hat? No. Remember, this is the tension, not the weight. The weight goes down, that's true, and we've put that here. But when you take out the j hats, you now have a magnitude equation. Now when you put the vector sign for the tension, you got to give the direction for the tension, which is directed upward. Okay, so this is your answer. Now, how does this change if the block is lifted at a constant velocity? Okay, so let's go ahead and draw our motion diagram. So now when we move upward, and just ignore that. Okay, so now when we move upward, I'm going to have it go like that. Okay, there's my velocity. Here's my acceleration. Okay. Does my free body diagram change? Let's look. No, I still have the string touching the block. I still have the earth acting at a distance. I'm moving at a constant velocity, but I still have no acceleration. This means I'm in equilibrium. If I'm in equilibrium, then my free body diagram isn't going to change. So does my answer change? No. Same answer. So the only thing that changes in moving it up at a constant velocity is our motion diagram. And remember, for a motion diagram, when you're in motion, you have 3 velocity vectors. And this correlates with the 3 pictures that you had to draw in time in your forces inquiry. That's why you had to draw it 3 times, because you have 3 velocity vectors for your motion diagram. So when you go back and look at your force inquiry, you're going to see that motion diagram just staring out at you now, which may not have been clear when you were doing it. Okay, so that finishes example 1.